Hello everyone, I hope you are doing well. So in today's video, we'll go through the 2017 chemistry exam part 1 short answer questions where we'll go through question 1 to 5. Like always guys, before I start the video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. Industrially ethanol is made by either two methods. One method uses ethene, which is derived from crude oil. Straight away, when you derive something from crude oil, it is non-renewable. We know straight away it is non-renewable. And the other method uses sugar such as sucrose and yeast in aqueous solution. In other words, this is actually a fermentation reaction. If you don't know, when we ferment glucose, it's pretty much the same thing. When we take sugar and we ferment it with yeast, pretty much the same thing. So this, straight away, I know this is renewable. Beautiful. So the production of ethanol from sucrose and yeast proceeds according to this equation. As you see, this is the perfect definition of a fermentation reaction. Determine the mass in grams of pure ethanol that would be produced from 1.25 kilograms of sucrose dissolved in water, and we're given the molar mass of sucrose. Nice and easy. So what I would first find is the mole of sucrose. So the mole of C12H22O11 is mass over molar mass. That's what we know. Mass over molar mass. Where we know our mass in this case would be 1.25 kilograms. Make sure you change it to grams, so you just multiply by 1,000. That will be 1250 grams divided by the molar mass, which will be 342, and that's going to give us what? So 1250 342, that gives me 3.65 mole. And now what I'm going to try to do is, by using mole ratios, I'm going to try to find the mole of ethanol. So to find the mole of ethanol, I'm going to take this mole over here, the mole of sucrose, and I'm going to multiply by this fraction, where the top part is what we want to find, the coefficient. So for example, if I want to find the mole of ethanol, I look at the coefficient in front of it, and it has a 4, divided by which one did I use. Right now, you know how we use the value for sucrose. Sucrose has a coefficient of 1. So it's pretty much 4 times 3.65. And that gives me 14.619 mole of pretty much ethanol. But we want the mass. And remember, so mass of ethanol is the mole times the molar mass. And so that will be what? Let me just run this part off. That will be 14.619 times your molar mass of ethanol, which will be, in this case, we have 2 carbons, so 2 times 12 plus 1 oxygen plus 6 hydrogens. And so this overall will give me, let me make this smaller because my space is actually gone. I've kind of took all this space. Let me take this smaller, right over there, something like that. Let me also take this, push it upwards a little bit, and okay, so and put this over here. We're nearly done. So what does that give me? So that times 2 times 12 plus 16 plus 6, and that gives me the mass as, so the mass of C2H5OH, so ethanol, is to how many actual significant figures? 3, because what we're using is, this one is the lowest that we use, which was 3 significant figures, which will be 673 grams. Easy. Question I. Let's have a look at this one. Complete the reaction by writing the formula for the reactant in the box provided below. So we have ethene plus something. Through a catalyst, we then get ethanol. So if we had ethene here, sorry, I even saying it, but so we have a double bond of ethene here. We have a H here, and a H here, and a H. The only thing that you can react it to create ethanol is actually H2O, because one of the hydrogens in H2O will go here, and the other OH, we know the for example, we would be left, because you've used already one of the hydrogens, so we would left with oxygen hydrogen, which will also go to this part over here and create an OH. This overall will create ethanol. So let me just write that. So plus that should create C. So C, H, 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 OH. Does that make sense? Yep, everything looks good. Yes, it does make ethanol. So adding water, so adding water, one of the hydrogens will go here, and that OH will also go here, and that's what it will create. So water, so complete the reaction by writing the formula. So actually make sure you also write the state. Well, because all of them are in gas, the water has to be in gas. Easy. Classify this type of reaction. Well, this is an addition reaction, because what we've done is you've added two molecules and you've only received one. For example, that's what you've done. So whenever you have two molecules and you add them together and you only get overall a one product, it's always going to be an addition reaction. When you add two stuff and you get one only product, well, that's an addition reaction. So easy. An addition reaction. Beautiful. So ethanol can be converted into ethanoic acid in the presence of a reagent X. Write the formula for reagent X in the box provided below. Of course, you should memorize these. Make sure you have to. So there is organic reaction pathways, which I would say absolutely memorize them. If you don't have this table in your actual, say for example, in your room, so you can memorize it, remember you need to memorize these formulas, these pathways for your exams, because you actually don't, these are not in your formula sheet. And as you can see here, I've nicely written one here that goes through all the reaction pathways. So what we're going from ethanol, which is an actual alcohol, to a carboxylic acid. So this here is, of course, alcohol. And to get to carboxylic acid, which is, sorry, it's really very bad here. But so for example, we're going from this over here, this alcohol, and we want to get to carboxylic acid. What is our reagent? Well, we use this one over here, which is Cr2O7. So this one over here, or this one. They're both the same, by the way. To get through alcohol to carboxylic acid, both of these two are the same. So these are your reagent. So that reagent overall is what? It is Cr2O7 minus AQS H plus AQS. Very, very, right, smaller. So there we go. Nice and easy to get full marks for that. Just make sure you memorize it. I would absolutely say that. Yeah. Easy. Let me write that, and that's it. Is that it? Looks good. Yeah. So ethanol can be used in the production of esters. Write a balanced chemical equation for the reaction of ethanol and propane-1 all using semi-structural formulas for all organic compounds. Okay, let's actually write this reaction. So if we're reacting ethanol, which is CCOH. Sorry, what am I doing? Sorry, ethanoic acid. What am I doing? So if I'm reacting this is ethanoic acid. If I'm writing ethanoic acid with propane-1 all, we are going to get an ester. So it's going to be CC, carboxylic acid, which has this over here, this acidic group. All right. And we're going to react it with propane-1 all. So propane-1 all is what? So propane-1 all is, so writing to 3 cis, because that's propane. And at 1, it has an OH group. So I'd say this is your OH group. Nicely written it. So it will look like this. Done. So if we add these two, what happens? So if you add that, make sure, like, imagine reversing this to make sure the alcohol group is on this way. So so it'll be HO, C, 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 H here. All right. All right. This is what we're going to do. If we're adding these two over here, we're going to actually have these two actually react and produce water. So this here will give us water when we're trying to do an esterification reaction. So these both the carboxylic acid and the alcohol will react, and they will produce water because this here will be taken out, and so there will be a bond formed. So let me take this at the bottom here. There will be a bond formed, plus also a bond that will be formed, which is C, C, double bond, O. So I'm writing this part over here right now, but with a new bond, which is, so imagine taking this part out, because that's water, and putting these two, combining these two bonds. So we get C, 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 H, 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 and H. All right. And that is it. That is your actual reaction over here. So if we want to write it in a semi-structured formula, all we got to do is rewrite it how it's written. So write this first part. So your carboxylic acid, which is CH3 COOH. And if you don't know, carboxylic acid in kind of your temperature is always liquid. The way you know is just looking at your data booklet. Have a look at this part of the data booklet if you don't know the states sometimes of these stuff. If you look over here, as you can see, I know that ethanol, this part here, well, it's ethanolic acid actually, but yeah, already like ethanol, propanol, these are all in liquid states. So because they're not gases. So yeah, so I know for a fact it has to be in its liquid state. Plus this over here, plus, which is just CH3. I'm writing this one over here. It's easier to write than compared to that. So CH3CH. CH2 was it? So CH3CH2, CH2 OH. Beautiful. And also that's going to be in its liquid state. It's called propan-1-ol. And that is going to form, again, water. Because all of these are in liquid, water has to be liquid. Plus your ester group, which is CH3, COO, CH2, CH2, CH3 will also be in its liquid state. And that's pretty much it. I think that works. Done. Write the IUPAC name for the ester product of this equation. Easy. You should know whenever we're dealing with esters and when we're naming them, when we're putting them together, we're gonna have one part that is of course the alcohol group, and we're also gonna have where the carboxylic group was. So we're always gonna start with the alcohol group. What is the number of carbons that we used? Well, we got 1, 2, 3. So that is a propyl. So it'll be, your name will be start of pro. Pill. And now we start counting the number of carbons on the carboxylic acids, which is just 1 and 2, which is ethyl. So around ether, and we write it ethanoate. So if you had, if it was propyl, you write propanoate, or yeah, butanoate. So in this case, it will be ethanoate. So propyl ethanoate. Nice. And yeah, I think that's it. Question 2. A vehicle that is powered by a diesel engine is able to use either petrodiesel or biodiesel as a fuel. Petrodiesel and biodiesel are not pure substance, but are a mixture of molecules. In general, petrodiesel consists of molecules that are shorter in length on average than those found on biodiesel. Biodiesel contains molecules that include functional groups. The table below lists some of the properties of the two fuels. So we got both petrodiesel and biodiesel, and we've given the major components, so that's the formula, and the energy content and the CO2 emissions. All right, what do we know already about petrodiesel? We know that petrodiesel is just a straight chain. It's a straight saturated chain, a long saturated chain, and only the forces that are acting on it are dispersion forces. Biodiesel is much more different because it is longer, but also it has dispersion forces, but also a dipole to dipole forces because it has an ester group there, an ester group. So, but overall, we know that petrodiesel actually has a higher energy content than biodiesel. And of course, petrodiesel has a high CO2 emissions per kilogram of fuel used. So let's look at the question. Describe and explain the difference in viscosity under the same condition of the two fuels and how this would affect the flow of each fuel. You should straight away know that because biodiesel has an ester group. So first, let's talk about petrodiesel. Petrodiesel, okay, first, let's actually talk about viscosity. Viscosity is the rate of flow. If you have a high viscosity, it means, think of it as like honey. When you pour out honey, you know how it slowly goes down? It means it has a high viscosity because its resistance is high. Whereas if you take water and you pour it down, it has a low viscosity because it pours down quickly and it has no resistance. So viscosity that's what it means. We know that petrodiesel, because it only has dispersion forces, it has very weak dispersion forces and hence would have a low viscosity. Well, biodiesel both has dispersion forces but also a dipole to dipole due to the fact that we have an ester group and hence will have a higher viscosity. And also the big problem with overall with viscosity is having a high viscosity is a big problem, especially in fuel lines. If you're like in a cold climate, for example, in Antarctica, and use a car and you don't put petrodiesel, but you put biodiesel, and we know at cold climates what happens, the viscosity increases gradually, very highly. And what would happen if your fuel lines start to freeze because you poured biodiesel and they won't even run into the engine and it'll be just useful. That's why in those Arctic places they actually use petrodiesel because it has a low viscosity and it wouldn't even create any problems. So that is the main approach for that. So let's have now just describe the differences. I think I talked a lot, but that's what you just want to talk about. So describe and explain the differences of viscosity under the same conditions of the two fuels and how this would affect the flow of each fuel. Easy. So let me see if I'm just doing this. Beautiful. All right. So what we're going to actually say is, we know that So we know that biodiesel exhibits a higher viscosity compared to petrodiesel, making it less prone to flow easily. This is due to a higher viscosity arising from the strong intermolecular attractions, or actually forces is another better word, forces between biodiesel molecules longer carbon chain. So longer carbon, we know that biodiesel has a longer carbon chain as shown from here. So longer carbon chains in biodiesel molecules contribute to a stronger dispersion forces. Beautiful. So that it has both dispersion forces and also the presence and polarity of ester group, so the ester group in biodiesel molecules I think I'm just mumbling a lot, but molecules contribute to dipole attractions. These interactions overall increase viscosity, impeding, so it will stop impeding the flow of biodiesel in fuel lines, fuel lines. So impeding the flow of biodiesel in fuel lines compared to petrodiesel. Look, overall, I know it's a lot, but what I've done is I've kind of just put all this information that is very important to know. Of course, you just can dot point it, make easy 3 dot points, get the 3 marks, but I do want to make sure that I am showing you how to really, going in very detail to show you how to understand the concept. So that here is, we've explained what biodiesel, but now we just need to do one more dot point, which is petrodiesel. I know it's very long, and that's the key. I want to make sure I put a lot of content so you guys can read it and understand it and learn from it. And also petrodiesel, make sure in your exams you don't write it like this. Never write it in these big. Make sure dot points that are precise. 3 dot points that are nice and precise that will give the information that the examiner wants. So yeah, so we know that petrodiesel, with its shorter length, experiences a weaker intermolecular forces, which is only dispersion forces. Consequently, it flows more easily than biodiesel due to lower viscosity. Enabling smoother transportation through fuel lines. And yes, this is very detailed, and yeah, I hope you read it and really understand what the questions ask you. And don't write this, absolutely, this is too long, but I hope I've gone to detail. I've summarized everything very much in detail on what you want to understand from this question. And yeah, that's it. This should get you for full marks. Make sure you summarize it very much less. Make sure you dot point it. And yeah, that's it. Question B. Assume that the combustion occurs in unlimited supply of oxygen for each of the following calculation. Careful of the word here, unlimited. What do we know about unlimited supply of oxygen? If we have a combustion reaction that is unlimited supply, this will create a complete combustion, and hence we know that CO2 and H2O will be produced as a byproduct. Use the data from the table on page 18. Calculate the number of liters of biodiesel that are required to be burnt to produce the same amount of energy as 2.5 kilograms of petrodiesel. So let's first calculate how much energy is actually released by burning that 2.5 kilogram petrodiesel. So let's go to petrodiesel. Let's have a look here. Energy content. Petrodiesel, so we know it's 43 megajoules per kilogram. So let's write that, 43. So we know 43 equals megajoules per kilogram. So 43 megajoules per kilogram. So if we know we have 2.5 kilograms of that biodiesel, so we can sub here 2.5. And so multiply these together to get the megajoules, the energy. We will get, so 43 times 2.5, we will get approximately energy as 107.5 megajoules. And that's how much energy we want. We want to know how many liters of biodiesel that are required to be burnt to produce this amount of energy over here. Which now, okay, now let's use the biodiesel for, energy content, which is this 38 megajoules per kilogram. So 38 megajoules per kilogram. And so because I know the energy, I'll rub this out and let's write that energy. So 107.5 in megajoules. And so let's solve for kilograms, which is just 107.5 divided by 38. And that will give me a mass of 2.828 kilograms of how much we need of biodiesel. But be careful, we want to make sure we have it in liters, and we are luckily given the density of biodiesel. So again, let's make a formula for this formula. So it's 0. That's right here. So write the number, so 0.89, and have a look at the units. So it's kilograms per liter, so kilograms per liter. And so we have the kilograms, so let's sub that on top. Let's rub that out. And so it'll be 2.828. And let's calculate liters, which is just 0.89 divided by that. And so we get how many liters? We get to how many actual significant figures? Well, the lowest significant figures in this question that we used are actually 2 significant figures. So it will actually be 3.2. 3.2 liters. Easy. What am I, just volume, am I writing volume here? Volume is equal to 3.2 liters. Easy. Calculate the mass of carbon dioxide, CO2, that would be produced from 3.19 kilograms of biodiesel. So we want to know the mass of carbon dioxide. Let's have a look at it here. So we know that the mass of biodiesel that, the amount of CO2 per kilogram of CO2 produced from each kilogram of fuel burn is this, 2.52. Yep, so 2.52 is, what is the units? So 2.52, it's kilograms of CO2, so the mass of CO2 over the mass of the fuel. And so we know we're using, how much is the mass of fuel? We are using 3.91. So 3.91, and so we multiply these together to get the mass of CO2. Easy. Your mass of CO2 is 3.91 times 2.52, and we get to how many significant figures? We want it to, in this question we use all 3, so it'll be 9.85. 9.85 kilograms. Easy. Have I made any mistakes here? Looks all good, yeah? We got that. We got the number of liters. Okay, that's all good. Question C. In some circumstances, there is a limited supply of oxygen. When we have a limited supply of oxygen, what happens? There's a problem. So when we have a limited supply, we have an incomplete combustion, and we will produce normally H2O. We can also produce carbon monoxide or soot, which is just carbon. And so these are the kind of combinations we get. So in the question, write the balanced chemical equation for the combustion reaction of a major component of biodiesel, which is this, where carbon monoxide, CO2, is the only product containing carbon. So we're not actually creating soot, we're only creating water and carbon monoxide. Easy. So C19H32O2. Now for a fact, I know that biodiesel is liquidy. So it's going to be in liquid state, plus oxygen gas, which is in its gaseous state, goes to H2O in its gaseous state, because no, actually it's in liquid state, because if this is liquid and we're reacting with oxygen, yeah, it's liquid, plus carbon monoxide. Make sure it's carbon monoxide, and that's going to be in its gaseous state. So how much do we have carbons? We have 19 here, so we need to get 19 here. So now how many hydrogens on the left side? We have 32, so we need 16 actually here. So if how many oxygens do we have on the right? We have 16 plus 19, which is 35, if I'm not mistaken. Is that right? Yes, it is. So 35 on the right. How many oxygens? So 2 plus 2. No, it won't work because there is a even number of oxygens and we have an odd number of oxygens. It wouldn't work. So we have to actually double those hydrogens. So what I'm going to do is I'm going to rub this all out. I'm going to double this part here. So now we have 38 carbons. So 38 carbons. And so how many hydrogens? We have 64. So we have to write here 32. So we have 32 times 2. Yep, 64. And so how many oxygens? We have 2 times 2, which is, of course, 4 plus 2. So we have 6 on the left-hand side. And we have here 32 plus 38, which is 70. And so 70 minus 6, that will give us 64. And if I divide this by 2, we get... What's happening with me? Really? It's something wrong with me? 32, yep. That will give me 38, yep, 670. 4, 2. Have I made a mistake? Yep, got that. H2O. Looks good. And so... Not minus, it's a minus 4. Sorry, minus 4 because... So 2 times 2 here, 4. And we also don't include this, so 4. It will be 66 divided by 2, which is 33. So this part would be 33. So let's see if that makes sense now. Let's see if everything works. So how many hydrogen, how many oxygens do we have on the left? We have 2 times 2, that'll be 4 here. 33 times 2, which is 66. Adding these, we get 70. And also this one, we have 32 plus 38, which is also 70. Great, that works. Wow, that took quite long, but yeah, that's your answer. Does that look good? Yep, looks good. Question 3, let's have a look at this. Liver cells can store excess glucose. Name the polysaccharide that is used to store excess glucose in the liver. If you don't know this is glycogen. Remember, what is glycogen? Glycogen is, for example, it is the storage of glucose. For example, if you eat like a big amount of meals, say you eat a large meal and you have a lot of glucose in your bloodstream, and so what your actual body does is it stores it. Your liver actually stores it as glycogen, which is this big polysaccharides, filled up with glucose, of course. And the way it's formed is through glycogenesis, which you don't actually know, that's in bio. But what pretty much glycogen serves as, it's the storage form of glucose. It's just the storage of glucose. And it's like it'll be readily available when, for example, your blood sugar drops. So what your body will actually do is break it down so you can get glucose into yourself. Or, for example, you just go on, you run around a lot, where you need an increased energy demand, and that's what your liver will do. All that storage of glucose will be broken down again to glucose, and you can use it. So your liver cells, the polysaccharides that actually stores it is actually called glycogen. Easy. Glycogen. Name the bond connecting two glucose units in a polysaccharide named. That's called a glycosidic linkage. Glycosidic linkage. Beautiful. Glucagon is a peptide hormone that works with insulin to help regulate blood glucose level. Glucagon acts to increase blood glucose levels through targeted action of the polysaccharide stored in the liver. Glucagon consists of chains of 29 amino acids, the sequence in which is given below, and folds to the form of the short alpha helix. Alright, we've given a big chain here of 29 amino acids. Of course, we have the terminal group of an amine group here and the carboxylic group. Draw a diagram of the structure of the section of the glucagon peptide shown in the box in the amino acid sequence. So we want to draw this part over here. So let's do that. We have methionine. So first let's draw that methionine. How would that look? So methionine, which you will find down here, met, which is here. So met is this part here. Let me just, I don't want that, that's that one. So so what we're going to get is, we're going to get, at the end of the terminal, be careful. At the end of the terminal, we're still, it's going to have an NH. So imagine like have leucine still, but you're not with it. So it's like cut off. So you want to put a bond here. So imagine you would have normally like, a carboxylic acid with leucine, but imagine you're breaking that bond because we're not including leucine, but we want to include this bond. It means that it still has that bond. It was connected to something. So that equals CH. So this part CH. Wow, it's a long one. So CH2. So the branch CH2, S, and CH3. Yep, and so that looks, yep, so in a CH, yep, that's, actually, let me write the CH right over here. We'll make it nicer. CH here. And so, and then we have, of course, the carboxylic group. And so, again, so that, and then what's the next one that we'll go with? ASN. ASN's what? Asparagine, which is this one over here. Let's highlight that too. So this one over here, again, you're going to have this amine group. So yeah, peptide linkage here. You have a CH here. You have, of course, your carboxylic part here. And let's draw the side group, which is a CH2, a C, double bond O, and a NH2. That looks great. Next one is THR. So THR, which is, where are you? For this one over here. Let me highlight that. So drawing this one here, because we're going to get an N group, CH. And so, of course, we're going to end it because we have COOH here. So COO. Very nice. COOH. And so what about the side group? So we have a CH. We can write an OH here. And this one over here is CH3. That's it. This looks great, actually. If that's right. Have I made any mistakes here? That looks good. Looks good. Yeah, it looks actually quite good. And make sure you have that part over here, because remember, it's not like, it was, you straight away should know that it was bonded already. There was a peptide linkage over here, but yeah, it's like it's not there anymore, but we still have to put that there. Easy. Describe the bonding that is found in the primary and secondary structure of glucogen molecules. Okay, first of all, when we're talking about the primary structure, it's all about that peptide linkage. Those what we call those covalent bonds. These are our primary structure. For example, in this thing here, our peptide linkages, which is this part over here, and for example, this part here. These over here create a covalent bond. They're actually covalently bonded, those peptide bonds. And that's what our primary structure does. It is this straight chain, and that's what our primary structure comes from. When we're talking about the secondary structure, so there's two secondary structures. There's, of course, the alpha helix and there's the beta sheeted. When, in this case, we are given the actual hint that it is a short alpha helix. And so whenever we're talking about a secondary structure, it's all about the hydrogen bonding. It's all about those hydrogen bondings. And in this case, the hydrogen bonding will always occur. It always occurs with this in this one group of carboxylic, this oxygen group, and the carboxylic acid right over here. It will form a bond with another amino acid. For example, imagine this is your first amino acid, of course. What is the next amino acid? This one over here. It will form another with another amine. So, for example, this is your amine here. It will form hydrogen bondings with this amine group over here for stability. So, for example, imagine you had like a nice swirly, and this is what an actual beta sheeted is. You would have some bonding that will occur, and these are the bondings that are occurring. A hydrogen bonding occurrence between the, for example, you have a carboxylic acid with another amide group. And yeah, that is it. That's what you just need to describe. And what does it do? Well, it creates stability. For example, for the short alpha helix, the hydrogen bond creates stability, and it creates this spiral structure. And yeah, so we can just talk 3 marks about that. Let's do that. I'm going to be in very detail. Again, don't write this. This is just so you can read it and be like, so this is what it means. This is, okay, I'm going to dot point this. This is what I need to learn from that. I'm going to just go in detail, and yeah, hope you learn this. So what I'm going to first write is, okay, in primary, so in the primary structure, which, is of course covalent bonds, or your peptide linkages, the primary structure is defined by the sequence of amino acids linked together by peptide bonds. And so these peptide bonds, which are your covalent bonds, so these covalent bonds form between the carboxylic group of one amino acid and the amino group of the next amino. So, and the amino group of the next amino acid, And yeah, this is just for the primary acid in that chain, So this is just detailed for that, all talking about the primary structure, and it's very detailed. Now let's talk about the secondary. I'm going to make this little, actually, so I can fit everything in. I'm going to make this very little like that. And so, yeah, I'm going to, actually, how do I put this? What I'm thinking is I'll put it at the bottom right now, and I'll come back to it when I've written the next one. So now we're going to talk about the secondary structure. So in secondary structure, remember, it's all about the hydrogen bonding. So in the secondary structure, which are, hydrogen bonding, which are your hydrogen bonds, actually, glucogen folds into a alpha helix, into alpha helix secondary structure, this folding is stabilized by hydrogen bonding. So stable by hydrogen bonding formed between the carbonyl, so this carbonyl part here, so the carbonyl oxygen of one amino acid and the amide group of another amino. So amide group. So and the amide, an amide hydrogen, not group, an amide hydrogen of another amino acid and so these create the spiral structure, contributing to stability, contributing to the stability of the molecule, to the stability of the molecule. And I think that will be it. Yeah, that's very detailed, and yeah, I think that should give you the mark 2. And yeah, I think that's it. So this is very detailed. These 2 marks, these 2 big, oh my god, these are very big. I'll be honest, not great, but yeah, make sure to take notes of these, and these are very detailed and go through the whole question. So I would absolutely put these somewhere. I'll put these right over there just for you guys to check them out. And yeah, next question. Explain why the amino acids serine and glutamine are not needed in the human diet, whereas histidine and threonine are needed. Straight away, this is easy. What do we know? So if we don't need some amino acids like serine and glutamine are not needed, these are called what? They are called non-essential amino acids, because what our body does, it produces them by itself. So our body produces them, and so we don't actually need them from, you know, a diet or something. But there are some, for example, histidine and threonine that we need, and we need to actually get it from a diet. For example, you know, we have, for example, vitamin C, which is so vitamin D is well, I believe it's not like it's called essential, but it's not an amino acid, of course. But like, for example, vitamin D is called, it's very essential, and so we need to take it from our diet, like fruits, oranges, and yeah. So when we don't want amino acids, when we have amino acids that we don't need in our diet, these are called non-essential, because they're not very important, because our body creates them by itself. And there are, of course, essential amino acids that our body cannot even produce, and so we need it in our diet. And that's what we just need to explain. Easy 2 marks, straight out. Nice and easy 2 marks. Let's write it, just see nice. So we can say that serine and glutamine are non-essential. So non-essential amino acids. So they are non-essential amino and can be manufactured by the body. Histidine and threonine, I can't even say that, are called essential amino acid. Are called essential amino acids and cannot be created by our bodies, and hence must be taken by diet. Easy. And yeah, now we're up to question 4. So let's try question 4. Question 4. Sulfur trioxide, SO3, is made by a reaction of sulfur dioxide and oxygen in the presence of catalyst. According to this equation, I love this equilibrium equation. I love equilibrium. It's one of my favorite topics to smash out. And so we know it's exothermic. In a closed system, in the presence of a catalyst, the reaction quickly achieves equilibrium at 1000 Kelvin. A mixture of 2 moles of SO2 and 2 moles of oxygen gas are placed in 4-liter evacuated sealed vessel and kept at 1000 Kelvin until equilibrium was reached. At equilibrium, the vessel was found to contain 1.66 mole of SO3. Calculate the equilibrium constant at 1000 Kelvin. Beautiful, easy question. You should straight away realize we're going to have to use our ice table here. So what I would do is write this whole equation on top of here. So 2, let me write it nice here. So 2 SO2, we don't need to stay. So oxygen goes to 2 SO3. We're going to write ICE, ice table. So I means initial. So what is the initial mole of the substance? So we know the initial mole of SO2 is 2.00. We know the initial mole of oxygen gas is 2.00 also. And we know the initial mole of SO3 is 0 because it's not even produced. It wasn't even produced at the beginning, of course, initially. But now we're looking at C means change. And change is, for example, if things are on the left side, in the reaction side, they're going to always have a negative because they're actually being lost. And remember, it all depends on the coefficient. So this will be negative because it has a coefficient of 2. You write 2x. This one here will be negative because it has a coefficient of 1. We write just negative 1x, which is just negative x. This one will be positive because we are forming it. So it'll be plus 2x because it has a coefficient of 2. And so we know at equilibrium, they told us that the mole of SO3 is 1.66. And so now it's a beautiful, easy question to answer. We know when you add these two, the initial and the change, it should equal to this. So if I added those, so 2x equals 1.66, your x value is 0.83. So what I can do is, again, if I add these two together, it should equal to our equilibrium value. So what we're saying is 2.00 minus your x, which is 0.83, which will give me, this part here will be 1.17. And so yeah, just keep doing it for the other one. So again, the next one is adding these two and should equal to equilibrium. So 2.00 minus 2x. So your x value, of course, is 0.83, and that's going to give us 0.34. 0.34. And that is it. We are nearly done. So just doing that, we've got our nice ice table. Of course, we want to make sure these are your moles, and we want to make sure we want to write them in concentration. So I'm going to write like concentration M, big M. So I'm going to write what concentrations there are. So remember, to get the concentration is just the number of moles over the volume, and we know the volume is 4 for all of them. So it's just 4 times your your number of moles divided by 4. So this divided by 4, this divided by 4, this divided by 4, and that's going to give us our concentration. So 0.34 divided by 4, that will give me, let me write it in a different color, 0.085. Is that right? 0.0. Yep. Next one, 1.17 divided by 4 gives me 0.2925. 1.66 divided by 4, that will give me 0.415. We are nearly done. So we got the actual concentrations, and now we're going to write our actual formula, our equilibrium constant formula. So we know our Kc is equal to your product. So what do we have our product? It's SO3, and it'll be to the power of 2 because that's the coefficient. And so it'll be also oxygen to the power of 1 because it has a coefficient of 1, and SO2 to the power of 2 because it has a coefficient of 2. Done. And now we sub all these values in there. So your actual Kc value is SO3, which is 0.415 squared, oxygen, which is 0.2925, SO2, which is 0.085 squared. So putting this all in your calculator, we should get 81.49, blah, 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 some big value. Well, because we use all in our calculator, what is the lowest significant figures? We used 2 significant figures. So it's actually just going to be your answer, your actual equilibrium constant is just going to be finally 81, pretty much 81. And make sure you want to know the units. To get the units, there's a quick way. All you're going to do is you're going to look at your product side and what's the coefficient, add all the coefficients. So we only have this part here, which is 2. This has a coefficient of 1, this has a coefficient of 2, so add them together, so that here's 3. And always product minus your reactant, so 2 minus 3, and that will be -1. So it'll be m -1 to the power of -1. That is it. Easy marks. B. A manufacturer of SO3 investigates changes to the reaction condition used in order to increase the percentage yield of the product in a closed system, where the volume may be changed if required. What change would the manufacturer make to the temperature and the volume of the system in order to increase the percentage yield of SO3? And justify your answer. So 4 marks. Wow. Let's see. So we can, fluctuate, like we could change our volume and our temperature. So let's have a look at this. Let's say we increase temperature. Let's say we increase our volume. That's our first one. Let's say we make up something, like we increase our volume. Increasing volume decreases our pressure, and our system's like, whoa, you've decreased our pressure. And I need to compensate for that. So I'm going to look, I want to try to increase that pressure. And the way to increase the pressure is by going to the side which has the more molecules. For example, this has 2 molecules, whereas this one has, 1 plus 2, which has 3 molecules. So it would go on the left-hand side. It will go to the left-hand side, which is a problem because that will decrease our yield, our product formed. So what does that tell us? Our volume has to be decreased. And that makes sense. If you decrease our volume, means you increase our pressure. Increase in pressure, your system's going to be like, whoa, that's a big change in that's a big increase. I need to decrease that pressure. And the way to decrease it is to go on the fewer moles. So on the side that has fewer moles, which is the SO3. Great. So let's just put that there. A decrease in volume is great. Now let's look at the temperature. The way to do temperature is by looking at the end flip change. Because we know the end flip change is negative, so it's exothermic, we know that energy is going to be released on the product side. And so think of it as just a molecule. And so let's say we increase temperature, so we increase this energy. What would happen? So there is too much energy on the right-hand side of the equation, and the equation is like, oh, that's too much. I need to decrease that. That's too much. So the way to decrease it, it's going to go on the left-hand side. It's going to go to the left, which is a problem because it goes to the left, we're decreasing the yield. So what we need to do is we need to decrease the temperature too. So we need to decrease volume and decrease temperature. Easy. And, we just explain it by using Le Chatelier's principle. And yeah, let's just write this question. Let's do this one here. So first we're going to say decrease in temperature. And explain why. Because it's 4 marks. Wow. So according to Le Chatelier's, can't even spell his name. I don't even remember Le Chatelier's principle. Decreasing the temperature, what would that do? So we know that decreasing the temperature of an exothermic reaction favors the formation of products. The formation of products. Since the reaction to produce SO3 is exothermic, lowering the temperature will shift the equilibrium, so shift the equilibrium position towards the right. This adjustment will increase the yield, will increase SO3 yield. And that's beautifully explaining the decrease in temperature. Now we just need to explain why a decrease in volume. Let's do that too. So a decrease in volume, and why? So if the volume of the system is decreased, the equilibrium will shift. So it will shift in the direction that produces fewer moles of gas. So in this reaction, 2 moles, so 2 moles of SO2 and 1 mole mole of O2 react react to produce 2 mole of SO3, therefore reducing the volume will favor the side we'll favor the side with fewer moles. Of gas, so fewer moles, which is the side of SO3 gas. And yeah, so that will produce a higher yield. Done. Yeah, that's it. And so question 5, last question. There are a number of structural isomers for the molecular formula. So the 3 of these propanol. So propanol is an aldehyde, we know that. Propanol, which is a ketone, and a propane in 1-ol, which is an alkene with an alcohol in it. The skeletal structure for this aldehyde propanol is shown. Write the semi-structural formula for the ketone isomer propanon. So whenever you're drawing a ketone, we know that the oxygen must be in the middle. So we have 3 carbons. So if I write 1, so let me just nicely, so 1, 2, 3. So of course the oxygen must be in the middle, always in the middle of the molecule. It cannot be on the side. So not in the middle, but like anywhere in between, but not on the right or left, because then it will be an aldehyde. So it has to be in the middle. And so write a semi-structure for the ketone propan 1-on. So it has to be that. And then of course these are just going to be your hydrogens, which yeah, we have 6 of them. Is that perfect? That looks good. That looks nice. And so write the semi-structures for this ketone propan 1. So it's just going to be easy. CH3, CO, CH3. And that's it. Draw the structural formula for the isomer propene 1-ol. So okay, first it's an ene, it has an ene, so it's an actual double bond. So it's a prop, so it has a 1, 2, 3. So at 2 it has already a double bond, so this at here, consider that 2. And at 1 it has an oxygen, so if imagine this is your 1, so you have oxygen. And is that it? Yes, it is. And then just everything put oxygen, so there'll be 1 oxygen here, of course 1 oxygen here, 1 hydrogen here, 1 hydrogen here. And yeah, that's it. So that is, draw the structure formula for that. Easy. The mass spectrum below was produced by one of these 3 named isomers. So, okay. Identify the fragment at 29 mz. So, 29 mz, which is here, it's actually your base peak. So, your base peak, and what do we know? So it could be, this fragment could be CHO, yeah? Does that make sense? Yeah, CHO, let's try CHO. That's one of the most common CHO. So we have carbon, which is 12, oxygen, which is 16, hydrogen is 1, that's 29. So CHO is one, yeah. So one of the fragments is actually CHO. CHO, and make sure it's a positive because it's an ion. It has to have a positive charge. So yeah, that's an actual CHO. That was actually good because remember there's only these molecules here, C, H, and O. So put them together and see if that, yeah, 29. Beautiful. Name the isomer of the C3H6 that produced this spectrum. So one of these ones over here. The way I think you would do that is by looking at this fragment, which of the 3 of those molecules would produce this fragment the easiest. So let's just have a look and see which one I think that kind of produces it much better. So, yeah, name the isomer that produces spectrum and justify your answer. So, let's have a look. Oops. Let's have a look. Let's go back to our think. So, having a look at this, we're looking at a C HO plus. Which one will give us this fragment easily? Having a look at this ketone, CHO. No, this one's rubbish because we have a CO here, but where's the H around it? So it doesn't even have a CHO part here. There's no H's anywhere bonded with that. Yeah, so no, it wouldn't be this ketone. What about this propane T1 all one? So CHO. So it has a. This could be a CHO here. That could be that one. Yeah. It could be fragmented to that. What about the next one? What about this aldehyde? So let me draw it nicely, this aldehyde. So that aldehyde looks like C, C, C. And so it has, of course, a double O here and H. And it looks like this. So that's your aldehyde. That's how your actual aldehyde looks like. So let's also have a look at this. How easy would this be fragmented? This will be easily fragmented. The CHO is right over here. CHO. It's actually your aldehyde, pretty much, propanol. Because think about it. So imagine it gets fragmented. So if the bonds get broken down. So if this gets broken down, this part is straight away the fragment. It's easily broken down. It's easily fragmented compared to the other ones. I mean, have a look at this garbage here. So this one, of course, could also be that one, but have a look at this. If we wanted this part over here, how many bonds do we break? We have to break this bond, break this bond, break this bond. So it's much harder to get this fragment over here compared to this. This is easily your aldehyde is easily broken to that fragment, propanol. And is that all right? Yeah. So. Because it can easily be broken down. I think with that, let's give you the full marks there. So name 2, that would be produced. So, so what we're going to write is propanol. Let me spell it again. So it's the propanol. Yep. Propanol. And why is that? So it's named the isomer that is produced this way, and justify your answer. So we know straight away that it's much easier to produce. So propanol, it's easier for propanol. So propanol, it's easier for propanol. Why is it much more? Has I decreased the width of the pen? I think I have, yeah. So it's easier for propanol to be fragmented. So to be fragmented to CHO compared to, what was the other ones? Propanon and proptune. So proptune 1-ol there. So proptune 1-ol. So that is why. So propanol is easier to be. So propanol, it's easier for propanol to be fragmented to this compared to this. This is actually hard to write because 3 marks for just this much writing. Propanol is easy. So propanol, it's easier for propanol to be fragmented to this compared to propanol and propanol. Yeah, because of course, propanon and propanol can be fragmented, but it's much harder for them to be fragmented to that. And so, I think one more to give the full mark, I would say, is to, justify it. This is also shown. This is also proven by the spectrum at 29 mz, showing CHO plus done. I think that will be it. I mean, there's nothing you can really write more than that. Propanol, it's easier for propanol to be fragmented compared to propanol and propene 1 all. This is also proven by the spectrum of 29 showing this. Yeah, that, I think that would be it for that one. Consider the, okay, carbon NMR and hydrogen. I love these ones over here. So we have straight away, having a look at this, we have actually straight away 2 carbon environments and 1 hydrogen environment. So identify which of the following 3 named isomers produce this NMR spectrum on page 24. Justify your answers referencing both spectrums. Easy. So if we have 2 carbon NMRs, let's have a look at our, which ones have 2 carbon NMRs. So two carbon environments. So let's have a look. Let's look at this one over here, the ketone. Okay, because of symmetry, we know that these 2 over here are going to be considered as 1 carbon environment, and this one also is going to be considered as 2. So this one actually fits. It has 2 carbon environments, and also we had 1 hydrogen environment. And it is actually 1 hydrogen environment because of symmetry. These hydrogens, because they're symmetrical, they're actually considered as 1. So this over here is great. It does fit into that spectrum. Let's have a look at the next ones. So we need to have, again, 2 carbon environments. Nope, this one has 1, 2, and 3. There's no actual symmetry. There's actually 3 carbon environments, and whereas this one over here is 1, 2, and 3. Also, this one has no symmetry. So this is actually a nice and easy question. It's actually your ketone, which in this case would be your propanone. Yep. So that one. Let's write that down and justify our answer. 3 marks. Okay. Let's be very specific with this. So propanone, like that. So propanone. Yep. So propanone exhibits, because of symmetry. So we know it exhibits a symmetrical, symmetrical molecular structure. With equivalent. So with equivalent, we know we had equivalent in carbons from it, both sides, atoms, resulting in 2 distinct peaks, distinct carbon, so in 2 distinct carbon environments, and then we'll talk about the peaks carbon environment. Wow, I'm writing so quick that I'm writing rubbish, but the presence of 2 peaks in the 13 carbon spectrum indicates the existence of 2 carbon environments, Yeah, I think that will be it for that one, and then we can talk about in the next part. So furthermore, to prove more, propanone has only 1 hydrogen environment because all the hydrogens, I think, were symmetrical from both sides. Yes, which created 1. So because all hydrogen atoms are symmetrical, leading to a single peak, in 1H spectrum. So 1 spectrum, and so this again, I think that's it. I think we need to also explain why the other ones are probably not right. So let's be more like, and also, so the observed spectrum, so the spectra, we'll call it spectra, so displaying two carbon environments, and one hydrogen environment rules out the possibility. So rules out the possibility of the what was it again? So propanol. That's it. Propanol and was it 2-ene? So protein 1-ol or something. Yeah. And so it rules out which both exhibit. What was it? They exhibited 3 common environments. And yeah, first, overall, propanol is identified to be the spectrum one. Yeah, I think that should give you 3 marks. Being very, making it more short, of course, and being more specific. And yeah, and that is it for this exam. Of course, I'll do the second part after some time because it is so tiring doing chemistry exams. They are very long. And yes, absolutely, they get very tiring. So I hope you guys enjoyed this video. Make sure, to share it with your friends. And I hope you guys have a great day. And make sure you take care of yourselves. Have a great day. Bye-bye.